Welcome to Chemistry 111. We'll go ahead and continue where we left off last class. So we're starting the math portion of this chapter. We're going to talk about a new unit. A lot of chemistry happens to deal with both the microscopic and, in fact, nanoscale scale atoms and macroscopic. We're going to deal with how those two interrelate. Just like in biology, you would talk about like how proteins are being formed, how those proteins are becoming enzymes. Those enzymes are cutting down and breaking apart molecules. Those molecules are going to be used to generate ATP, which is going to be the energy that allows me to be shouting at you day after day in class here. That the microscopic cell is producing energy to get this macroscopic change. The same way we're going to have atomic level chemistry coming together, atoms colliding, bonds breaking to do this chemistry, and we're going to see large scale change on the visual level. And part of this is, how do we go between the two? How do we see this? And how do we deal with this? When we were first started about this, we talked about AMU, the atomic mass unit. It's a way to measure an individual atom. We had defined carbon 12 as exactly 12 AMU. But that is a little bit too light for us to actually weigh. So we're going to deal with a new concept called a mole, abbreviated MLL as a unit, the same way as kilometers is abbreviated as km. But a mole is a special number defined as 6.022 times 10 to the 23rd of an object. It's kind of like a number like a dozen. A dozen, everyone says it's 12. You could be a dozen eggs, that's the most common form, but you could be a dozen donuts. You could have a dozen students. And there's a number like gross. A gross is a dozen or 144 of something. And you may not remember it, but a googol actually had a meaning. Googol was 10 with 100 zeros, 10 to the 100th power. That's what a googol originally meant. And obviously it fits very well with Google's overreaching qualities here, where a 10 to the 100th power of search is. So a mole is 6.02 times 10 to the 23rd of something. This number specifically is called Avogadro's number, after a scientist, Amedeo Avogadro, who we'll talk about when we get to the gas chapter and the end of the semester. But it's named after him. So the constant n subscript a is the number of Avogadro, but it's 6.022 times 10 to the 23rd. Now, we will use this chiefly to convert atoms or molecules to moles and go moles back to atoms using dimensional analysis. If you're struggling with dimensional analysis, do reach out and talk to me. I'd be glad to try to help you. Email me, set up a time. I'll be glad to try to walk you through some of this, and we'll work some one-on-one. I know I'm going fast. I know online learning is not always easy. So find some time, reach out. I'll make time. We'll find a time that is mutually beneficial for both of us. And I'll walk you through it, because it's only going to continue. But so we'll start usually with our starting unit as a fraction over 1. And then we're going to multiply by Avogadro's number as the conversion factor to cancel out our starting unit. So our basic example here is, if I had 5 moles of carbon dioxide, CO2, we remember it's a bimolecular. C with 2 O's is carbon dioxide. But I wanted to turn 5 moles into molecules. I set up 5 moles over 1, and I'm going to multiply by Avogadro's number so that moles on top cancels moles on bottom, and what we're left with is only molecules. So I've set this up. This ratio, we could flip this around. We could use this either divide by 6.02 or multiply by 6.02, but this ratio of molecules per mole is always the same. And so I want to set this up so moles on top cancel moles on bottom, and we're left with units of molecules. So 5 times 6 is about 30. 30 times 10 to the 23rd puts that at 3.01 times 10 to the 24th. Going backwards, 3.18 times 10 to the 25th carbon, atoms of carbon. How many moles of carbon? So I'm going to set this up Avogadro's number, atoms of carbon on bottom, moles of carbon on top. So atoms cancels atoms. We're left with moles. Now, before we go any further, I want to show you something. We want to double check this. So 318 times 10 to the 25th. Yeah. Okay. Going to switch to the big screen. Okay, let's see. Okay. Yeah, it's vaguely visible. I think I need a fatter marker, but if I'm doing this, 6.022 times 10 to the 23rd. If I'm setting this up, I want to make sure I'm punching this into the calculator right. Because what I'm doing, if I type it in like this, divided by 6.022 times 10 to the 23rd, I could potentially get something way, way wrong. Way, way wrong. And that we're going to get a number potentially to the 47th power. Because order of operations, it's going to say 3.18 times 10 to the 25 divided by 6, but then multiplied by 10 to the 23. So if you're going to type that in, for God's sake, put a parentheses around those. And think, if I divide by a big number, you should get a small number. We shouldn't get a way bigger number. So double check that. An easier way to type this in would be 3.18 EE 25 divided by 6.02 EE 23. If I do that, that's going to keep these two terms together. And you're going to keep the number at a normal ratio. So be careful when you're typing this in. Think about your options. That's why I say, try to reason out, does this seem like a reasonable number? If I divide a big number by a big number, I should not get a bigger number. So sometimes you can look at your result and go, ooh, something went wrong. Sometimes you can if you think about it. Not always easy. Takes practice. But sometimes if you're constantly questioning yourself, that helps. Okay. The next concept we'll need is molar mass. So we talked about the atomic mass of an individual atom, such that atomic mass is 1 AMU is actually converted into grams by a factor of 1 AMU is equal to 1 over 6.022 times 10 to the 23rd grams. What that means What that means, the conversion of atomic mass units to grams means that carbon 12, which is exactly 12 AMU, 1 mole of carbon 12 would be exactly 12 grams. We set this up in such a way that AMU and moles give you, they're interchangeable. You can use AMU to look at 1 atom of carbon, or grams to look at 1 mole of carbon, and the results would be the same number. So we're going to use the periodic table to look at both molecular weight. Molecular weight is of a molecule, and molar mass, which is in grams per mole. To calculate molar mass, we are going to because we're dealing with a bunch of isotopes, we're going to have to take the average atomic weight, the molecular weight, the weight which was the weighted average. So instead of carbon 12, we'll use 12.01. Instead of boron 10, would have boron 10.81. Instead of like chlorine 35, would have chlorine 35.45. So we'll use the weighted average that we talked about in chapter 2, which appears below each element at the periodic table. Don't worry about memorizing these numbers. You will always have a periodic table to go back to. You always have a periodic table to go back to. So you can always come back to that. I will know a certain amount of those values because you use them enough, they get embedded in your brain. I'm going to try not to use crutch words, but it is very, very hard. But to calculate the individual molar mass, we're going to take the sum of all of the atoms and multiply by their subscript. So for carbon monoxide, carbon is 12, oxygen is 16. The molar mass of carbon monoxide would be 12 plus 16, or what? 28. Carbon dioxide, as we'll see on the next slide, would be 12 plus 16 plus 16 because there's 2 oxygens. So 28 plus an additional 16 would be 44. We need to be able to easily and reliably calculate the molar mass of each atom, and we're going to do that in a slide or so. This is a quick shortcut. One thing to note about this book, about chemistry in general, almost everything will go through moles. If we have atoms, we're almost guaranteed to go through moles. If we have grams and we're looking at of an individual atom and it's not density, there's a good chance we'll go through moles. If we're actually doing real chemistry and not just measuring properties, we will probably go through moles. So we need to be able to convert. From moles, if we multiply by the molar mass, we'll get mass. Moles, if we multiply by Avogadro's number, we'll get atoms. And we're going to add to this later in later chapters, but for now, these are the 2 major conversions we'll need. So if we're going backwards, obviously we'd have to divide by those constants. You could memorize those relationships. I hope you won't have to, because dimensional analysis always has us canceling out the last unit, getting to the new one. So there's no equations you really have to memorize if you can cancel units. The best way to learn this is to see some examples. So 3 moles of CO2. How much would this weigh, and how many molecules would there be? 3 moles. So, as I just said, to calculate the molar mass, we have 12 from carbon. Technically, it's 12.01. Oxygen is 16. Technically, it's 15.999. But for all intents and purposes, with 3 moles, our sig figs are only really 1, maybe 2 if I say 3.0. So these rounding errors, 12.01, aren't going to change much. Because there's 2 oxygens, I have to double that, which would give us 44 grams per mole. Now, setting that up, 3 moles, and I want moles on bottom, so I have to multiply by 44 grams. I do that, and I'd get 132 grams. The important thing is my moles cancel with my moles. And that gives us our answer in grams. How much does that weigh? Same starting point, 3 moles. How many atoms would there be? I still want to cancel moles, so I need Avogadro's number now. 1 mole is 6.022 times 10 to the 23rd. 6 times 3 is 18. Basically, 1.8 E24 is the answer. E24. So moles cancel moles, and you're left with molecules. Quick practice. Let's do with water. This is putting 2 conversions together. If I have 36 grams of water, how many molecules are there? In lab, we weighed about 10 grams of water to do that density of water. You saw about how much 10 grams were. So imagine we just about tripled that. 36 grams of water. How many molecules are in there? So 36 grams. First thing we need is, what is the molar weight of water? How many grams? Well, hydrogen is about 1. It's like 1.007 or 1.0, something like that. Really hard to see. Essentially, it rounds to 1. There's 2 hydrogens. So 2 plus 16, 18 grams. Conveniently, 36 and 18 are perfectly divisible to give us 2. Setting up the second step. 1 mole is 6.02 times 10 to the 23rd. 2 times 6 is 12, so 1.2 E24. I'm blocking the camera most likely. Yeah. 1.2 E24. Long story short, I left that in improper notation on the slide. But that would correct itself to 1.2 times e to the 24. So that is 1.2 septillion atoms. 1.2 septillion atoms. That is a lot of atoms in 36 grams of water. We're dealing with incredibly huge amounts of our substances. So when we do this, it becomes very convenient to turn this into moles. 2 moles is that many atoms. And yet here we are able to look at it. We're able to pour 36 mils into 36 grams, which is about 36 mils, into a graduated cylinder and hold it in our hands and deal with it. Not had to worry that there's more atoms there than there are like fish in the sea. So, okay. Where's my mouse? Okay. So the best thing to do is do some honest to God practice. So is my crutch word, and I'm so sorry for it. And I did it again. What is the molar mass of iron oxide? What is the molecular weight of potassium permanganate? And how many molecules are in a quarter of a mole of potassium permanganate? Molecular weight and molar mass can be calculated the exact same way. Exact same numbers from the periodic table. The only difference is one is AMU per atom in molecules, and the other one is grams per mole. In order to calculate this, we need a periodic table in front of us. Fortunately for you guys, I've already done this yesterday, so I remember the masses, so I don't need the periodic table. But when it comes to you guys, I don't expect you to know these. You do it enough times, your brain can hold these things in your brain and keep it with you. Iron is like 55.85. For the sake of this, I'm going to round it to 56. 5, approximately 56. It's going to make our math easier. Oxygen, as I said, it's 15.999. 16 is probably good. I wouldn't suggest you rounding them on the homework if you can, or at least if you're going to round it to maybe the second decimal place. But if I'm doing mental math, rounding this right now is so much easier. Oxygen rounds to 16, but 55.85 is probably a better number to use than 56. But in iron oxide, 2 irons, so 56 times 2, and 3 oxygens, 16 times 3. 56 times 2 is 112. 16 times 3 is 48. And before you're impressed or whatever about that speed of math, I did it yesterday. And even then I've done 16 times 3 a billion times because there's so many compounds with O3 in it. You learn these patterns. So 112 plus 48 gives you 160 grams over moles. Straightforward. I read these numbers off the periodic table, or I would have had I not literally done this yesterday. Potassium permanganate, on the other hand, different compounds, different weights. K, potassium. MnO4, that's a weird oxyanion I mentioned. K, 39.1. I'd like to say manganese, we'll see if this works, is 54.9. I could be remembering that wrong, but we'll check. And oxygen, still 16, but 16 times 4 now. 16 times 4 is 64. 54.9, that's 80, 93, 94. 94 plus 64 is 158. Completely different compound. It just coincidentally weighs almost the same mass. Coincidentally weighs almost the same mass. But that would be units of AMU per molecule, because we're looking at the molecular weight. Hooray, we calculated this. Finally, how many atoms would be in a quarter mole? Quarter mole. So starting from 0.25, we just calculated the 158, but because of Avogadro's number, because of the relationship of atoms to moles, we do not need that. We are converting this, molecules. We are converting this directly. The Avogadro's number is like death. It does not care what you're dealing with. It's always the same. Doesn't matter if you're dealing with one atom of carbon or one molecule of potassium permanganate. The number is the same. So a quarter mole of carbon would be the same as a quarter mole of potassium permanganate. 1/4 times 6 is going to be 1.25. What is it? 1.5. 1.5. I'm rounding for the sake of our brains. 1.5 times 10 to the 23rd. And that would be our result. Back. Okay. You can go back later, look at, oh, here's the actual numbers, not rounded as heavily. But for the sake of our brain, rounded these to make the mental math a little bit easier. Percent composition is the last real math concept we'll teach. We'll use this to find empirical formula in a minute, but percent composition was something we kind of did in lab. We did this in lab. Everyone by this point has had lab or during quarantine. But if you've had lab 2, we dealt with percent composition. So how do we calculate percent composition? Percent composition is looking at the percentage of something in the overall total. Depending on what we're caring about, the mass percent is going to be the mass of the element over the total mass. In lab, we talked about the mass percent of this compound in this mixture. So we looked at how much mass of, say, silicon dioxide did we recover? And then we looked at what was the original mass of the overall mixture. By dividing the two and times it by 100, we got the percent of that compound in that mixture. In the case of percent mass of an element, we're going to look at the mass of the element divided by the total mass of the compound. In iron oxide, it's 77% iron, and well, that's iron 2 oxide. And iron 3 oxide, it's 70%. So how is that calculated? How is that calculated? Real quick. Iron, as I said, is 56. And iron oxide, 56 plus 16 is 72. So 56 divided by 72 times 100. would be how we calculate the mass percent and how we get the 77.8%. In the case of iron oxide, well, we have double the iron. So we said 112, and we already calculated the mass of this, 112 over 160 times 100. Even though we doubled the iron, we tripled the oxygen. Even though oxygen is a small component, tripling rather than doubling leads to a decrease in the percentage of iron. And that gives us why we have 70% instead of 77. We will also use percent composition to calculate the amount of a given, use it to calculate the amount of a given element present. We can also use this to go from a predicted percent to how much we should get. Where this is actually going to be super useful is when we have an unknown. All you biology majors, if you say you're out there looking, you find a new compound, you're going in the Amazon, you find a special type of beeswax that could be super useful for a drug, and you're like, what is in this? You're going to take it back to a chemist. The chemist is going to analyze this and figure out the percent composition of each atom, and so we can figure out the chemical formula of what all this is composed of. And when they combust this, they're going to get some type of percent composition of each guy, and we're going to use this to build the chemical formula. And that's what we're going to learn how to do pretty simply in a slide or so. The first thing is practice, though, before we move on, before we do anything else. Is practice. And in this case, in this top problem, 300 grams of mercury 1 iodide would have 183 grams of 0.8 grams of mercury. What is the percentage? In this particular problem, I've given you both values, so we don't have to actually calculate these. We don't need the molar mass in this particular case because I've given you the mass of a sample. So mercury is 183.8. We have 300 grams. We times by 100. And hopefully you recognize 150 would be half. So 183 is slightly above half. And then that would at least give us a hint whether we're on the right track or not, based on what number we get. 183.8 divided by 300 times by 100 to get it into a percent gives you 61.27. You could probably, 61.27. You might be able to round it to 61.3. But that is slightly over half. So that indicates it is a good chance it's right. Unless I did something horribly wrong or typed a number in wrong, it matches what logic dictates it should be. Now, this is a little tricky one. This one we're working backwards. We have a 50-gram sample of zinc chloride, and zinc chloride should contain 48% of zinc. How much zinc would be present in that sample? This is most useful for engineering people who are maybe working in metallurgy. You dig iron ore from the ground, iron 3 oxide, you dig it out. You have to put it in a smelter. You melt it down. You extract the pure molten iron out of there. If you know iron 3 oxide is 70% iron and you have 7 tons of iron oxide and you melt it down, how much iron should you be recovering if you're doing a good job? You should be able to calculate how much iron should you be able to get and how much iron can you be pouring into these plates? How much can you be dealing with based on the percent composition? If you're not getting that 70% of iron recovered, you get money being wasted. So the same way we can calculate how much zinc should we get if it's 48% zinc. We have to work backwards. So percent equals mass zinc over total times 100. That's our base equation. Plugging in our values, we have 48. Mass zinc is the thing we don't know. We have a 50-gram sample. This might be hard. This might be easy. Hopefully you've had some math. Hopefully you can rearrange this equation to solve for your unknown. We will have to do this on occasion. If you need practice, once again, come see me. We will practice. I will help you. I'm not so mean. I look mean. Maybe I sound a little gruff, but I'm not mean. Step 1, I divide both sides by 100. That gives me 0.48 equals mass of zinc over 50. Then, to both sides, I am going to multiply by 50 grams. And that will give me the mass of zinc is 24 grams. I should get 24 grams of zinc from that structure. So I rearranged the equation to solve for the unknown. That is something we have to be able to do, because I'm not going to always give you it the exact same way. If I give you one constant and this number, solve for that variable. If I give you density and mass, find volume. If I give you mass and volume, find density. If I give you volume and density, find mass. You need to be able to do whatever one I solve for, because if you only know one, you have a 1 in 3 shot. You might be able to get a slightly more than 1 in 3 by using the most common, but there's no guarantee that it's always going to be the same way. We will go, we'll maybe finish this slide, maybe go on the next slide. I don't know. I just want to look. Yeah, we'll try to finish up on this slide. So this is the final concept of this chapter. We will finish up this concept on Monday and start looking at test stuff and homework stuff and all that. But the empirical and molecular formula. Now that we have percent composition, we know how to find mass, mass percent, molar mass, moles, all that. We can look at more along the lines of chemical formula. The molecular formula is pretty much everything we've been dealing with for the most part. The actual number of atoms of a given element in a molecule or a compound. The most common example, the one I used yesterday, is glucose. For those in biology, glucose, one of the most common molecules in the body that you're going to deal with. What is the chemical composition of glucose? Just for the sake of us, I'm going to go ahead and say C6H12O6. There are 6 carbons per every 12 hydrogens per every 6 oxygen in glucose. It's a 6-membered ring with a bunch of OHs coming off of it. That is the molecular formula. However, you burn glucose, you won't see C6H12O6. You will get the simplest whole number ratio of all the atoms. You will simply get the ratio that for every 6 to 12 to 6, you have a C1H2O1. That for every one carbon, there is one oxygen. For every one carbon, there's two hydrogens. And that's what's called the empirical formula. It's the simplest whole number ratio of each element. Empirical, coming from the idea of observable. What is the empirical facts? What are the facts that we can readily determine by just looking? What is the empirical formula? When I burn this, I don't get how many moles are in there. I only get, well, I have 500 carbons for every 1,000 hydrogens, which is a 1-to-2 ratio. I have 500 carbons for every 500 oxygens, a 1-to-1 ratio. I'm only going to get the ratio between the two. Now, sometimes the empirical formula is the same as the molecular formula. As in, water is a 2-to-1 of H2O. But sometimes they're different. If I have hydrogen peroxide, it's a 2-to-2 ratio, which simplifies to a 1-to-1. And sometimes compounds will have the same empirical formula, and we'll deal with that. So glucose is C6H12O6. Xylose, which is a 5-membered sugar, is C5H10O5, which simplifies to a 1-to-2-to-1. Same empirical formula. In fact, formaldehyde has the same empirical formula of a 1-to-2-to-1. Formaldehyde is C1H2O1. It is a carbon bound to two hydrogens and double bonded to an oxygen. When you get to organic, if you have to take organic, you'll learn about formaldehyde. But it's a basic 1-to-2-to-1. They all have the same empirical formula. And so how are we going to determine the difference? And that's what we're going to be talking about on Monday. In fact, some of our molecules can only be represented as the empirical formula. Our salts, for example, can only be represented in the empirical formula because they are repeating pattern crystal structure. Sodium chloride, for every one sodium, there is one chlorine. But in a crystal of the salt, there's billions and trillions of sodium atoms and billions and trillions of chlorine atoms in just one grain of salt. So how do we deal with that? We have to simplify that. Even the sand we dealt with, silicon dioxide in lab, we dealt with that in lab. That is still the empirical formula. It's a repeating pattern of Si and O, where there's two oxygens for every one silicon. Even diamond and graphite are just the empirical formula that has carbon repeating over and over and over and over and over again in such a pattern that you can simplify it to just one carbon. Just one carbon. They're put together in a different arrangement, but for every way, there's just one carbon. With that in mind, on Monday, we will talk about how to calculate the empirical formula given either a percent composition or a mass of each atom. From there, we will learn how to get the ratio and then turn that into a molecular formula if need be. If need be. And that is will be the end of chapter 3. With that in mind, I thank you for sitting in on this.